So I will talk about how to bring this beacon chain light client data onto the network. Like the previous presentation showed how to access it over this REST API. And just to briefly understand what we are actually trying to put on the network, a couple key concepts that we need to understand. Like everyone knows the basic time units of the beacon chain. It's this 12-second slot, and the 32-slot combination of them is 6.5 minutes, is an epoch. So what Altair introduced last year is the concept of the sync committee period, which is like just a bit over 1 day. And this is the period at which the sync committee gets reselected. So in a block, currently we have a proposer who signs the block with a signature, and the signature is for the current block. And then the other ones can use this signature to verify that it's indeed coming from the proposer. And they also have to verify the entire block, and then they can apply it and attest to it. So the problem is you need to know the public key of the proposer to verify it, and the light client doesn't have that. So the light client needs an alternate mechanism to verify blocks. And this is where the sync committee comes in. It's an additional signature that signs the previous block. And they also not just sign the block randomly, but they also confirm that they actually did the verification. So if this sync committee signature, if there is like a higher than a 2/3 participation, the idea is that because it's a blockchain, you can trust the entire chain back to Genesis from the previous block. So there is a specification on GitHub in Consensus Specs repo that sort of describes the concepts, how a light client can use these sync committee signatures to sync with the network. But the problem is that specification, like you cannot just put those structures on the network as is. Like there is a lot of stuff missing. And also this REST API from Lodestar did a couple changes to it. So I will also have to do a couple changes here on the slides for the network presentation. So this data here, we want to put it on the network. So at the very basics, we need like this signature block, attested block, and put this in an object. So we have this optimistic light client header update, which contains the signature and some information about if it's from the current period and the next one, and the previous attested block with this parent root signature that we have seen before. So the problem here is still the light client needs a way to obtain the sync committee that is signing this. Otherwise, it's the same public key problem. So there is this concept of full light client updates that also include the next sync committee with a Merkle proof inside the structure. So as long as the light client can obtain any light client update per day, like per sync committee period, they can follow this next sync committee chain to verify the next one and the next one. There is still the problem at the start of each sync committee period that it's sort of unclear which of the forks will become the finalized one. So there can be multiple next sync committees. You only know that it's the finalized one once you have at least one finalized block in a new period. So there is also this concept of including the next sync committee from a finalized block. And then you have two Merkle proofs, like one of them that puts the next sync committee into the verified block. And then you have to verify this finalized checkpoint pointer from the previous block to the finalized block. And then you have to verify that this, also the signature of this sync committee for the attested block. So this structure is the full one that is also in the spec in this way. And I just like use this highlighting to make it clear like where the Merkle proofs are rooted, because that's always like one of the questions where it's unclear. Like the next sync committee is rooted in the finalized block to solve this problem at the start of a period. So combined with the other structure, like this optimistic light client update, there is still one piece missing, which is like the initial sync committee. And for that one, you usually configure the light client with a trusted block root. It can be any block root. of the last week's objectivity period would be best, but you can also use an older one. And that one can be used to obtain the initial sync committee and also the header to verify that it's in there. So these are all the structures that we want to put on the network. And then a light client themselves can use this to sync from a trusted block route to this light client bootstrap with the initial sync committee. Then they download one full light client update per period with the next sync committee until they are in the current period. Then they get a final one to get to the latest finalized head. And then they can just follow these optimistic light client updates to keep track of the latest slot's parent, so to say. You cannot get to the latest slot at this time. So the problem with light client data is servers do not really benefit from it usually, so it's difficult to convince servers to serve it. So what's happening here is that those structures are really small, like 25 kilobytes for a bootstrap or for an update, and the optimistic updates are just 300 bytes. So it's a very small network load, and then there is the problem that you need all of these Merkle proofs about the historic data, which is a bit difficult to compute on the server, so you should cache them. And this is about 6 megabytes for half a year, and it's bounded by half a year because the older data can be pruned. So the servers can serve this data for free. It's just static data for the history. It doesn't change anymore. And the latest one they have already in memory anyway. It's just a subset of the blocks. There is no proofs in it. So yeah, anyone can serve this protocol. And then what I did is I made a pull request to the consensus specs that basically puts this on the libp2p layer. So it's just like the 4 requests. You have the bootstrap request. You can get the best light client update for each period. You can get the latest one if you want the latest finalized head. And then you can follow these optimistic updates to keep track of the latest head. So this is the pull request here. If someone wants to comment on it or review it, it's welcome. Actually, this is already deployed on Prater and Kiln by Nimbus nodes. So the only change is that you use version 0 here and this underscore v0 suffix for the gossip subtopic. So this can already be used for experiments and it's fully functional. This REST protocol that was mentioned in the previous talk from Lodestar is also compatible with this. The naming is a bit different. So what's called snapshot in the Lodestar protocol is this bootstrap. The committee updates are like the full updates. The head update is the optimistic client update. But besides these terminology changes that still need some synchronization, it's functionally the same thing. It's the same structures. Conceptually, it's the same. So there is no additional concepts introduced here. It's just putting this same data onto libp2p. So now, how is this useful? Like, what can a light client do with it? And there is this additional fork that comes up soon, called the merge. And this incorporates an upgrade to the beacon chain called Bellatrix. And what it does is that it sort of it links the execution layer and the consensus layer together using this API, like the execution API. So during this, the beacon layer, the consensus layer takes over instead of the miners that suggest blocks. It's now this consensus layer. So there is the EL can no longer sync on its own because it needs a source to the latest blocks to use this existing efficient syncing mechanism. But the problem is also the consensus layer needs the EL to verify blocks because they contain an execution payload. So the CL needs a synced execution layer, and the execution layer needs the latest blocks to be synced. So right now there is this proposal called the optimistic sync. And in there, the CL starts by syncing blocks, but they only partially verify them, like they skip verification of this execution payload. And then they pass it to the EL. And then the EL can use whatever fancy mechanisms they have to sync to the latest head. And then you can verify the latest execution payload. And if that one is valid, the entire thing before is also valid. Again, because it's a blockchain. So the problem here is there have been some complaints about the complexity of this because it introduces this concept of partially verified blocks. And the Light client can help with it. So how can it help with it? So what it introduces is this fast access to the latest header. So you can get the latest finalized header and the latest optimistic header. And from that, you can just download the latest N blocks and pass them to the EL. And then it can sync. And from then on, you can just verify everything. So much simpler, you get the happy panda here. So what can also be done, like beside offering a replacement for optimistic sync, is that you can run an EL without a CL now, because the Light client itself is sufficient to sync the EL. And you get access to the finalized and optimistic ETH1 state roots as well through Merkle proofs. And the only thing that you cannot do with this is use the current head because you are always one behind. And this also means that you cannot really follow the validator duties with a Light client because you need access to the shuffling and also the current block. Like, yeah, the steering committee always sends the previous one. So to the other side, like what can happen is, can we run a CL without an EL? Like, yes. So you can also use this to just trust the latest finalized head and then use this like as your trusted checkpoint and sync backwards from there. So in this situation, you can get up to speed much quicker because you no longer have to verify the blocks fully. You only have to verify the proposer signatures. So you can get up to the current head very quickly if you initialize using this Light client sync protocol. This is useful like if you want to sync from the Altair start, or if you are offline for a couple days, you can get to the latest head very quickly, and as soon as you are there, you reconstruct the entire state, and you can do full validator duties if you also have a synced DL. Security-wise, it's very unclear like how to judge it because it sort of depends like how likely it is for the sync committee to accept bribes. So, but at the very least, there is no additional failure modes being introduced. So if the sync committee somehow convinces you to an incorrect head, the worst thing that can happen is that you get a beacon chain notification on your phone that says that you are no longer attesting to the correct chains, like misattestation, and then you just do whatever you already do when this happens. You just resync without this feature. The same as if you start from outside the week subjectivity period, which is only like 2 weeks, it can also happen the exact same thing. So to summarize, the Light client data, these bootstrap, the updates are very small objects. Anyone can serve them. They can be put on P2P and REST. I heard that there is also like a JRPC one from Prism, I think. They can also be put into the portal network, relatively straightforward. And the use cases that we get from this is that it is a solution for the optimistic sync. We can run standalone ELs without CLs, and we can accelerate the CL sync in case of downtimes or syncing new nodes, and we can get to the validator duties much more quickly. So this is the Discord if you want to discuss this, and also the other specs from before. The QR codes are just linking there. Thank you.